Hello everybody. Today let us discuss the insertion sort algorithm. Insertion sort algorithm is used to arrange the list of a given elements in ascending or descending order. It is based on the algorithm design technique decrease and conquer. More specifically, decrease by 1 and conquer. How does decrease by 1 and conquer work? In decrease by 1 and conquer, given a problem of size n to be solved, we will reduce the problem to size n minus 1, 1 less than the given problem, solve the smaller subproblem of size n minus 1, and when we get a solution to the smaller subproblem of size n minus 1, we will establish a relationship between the solved smaller subproblem of size n minus 1 and the original problem of size n. Using this relationship, we are going to solve the original problem. How do we apply this decrease by 1 and conquer technique to insertion sort? So to sort n numbers in ascending order, let us assume, we are going to reduce the problem of size n, that is n numbers, to n minus 1. The subproblem of size n minus 1 will be sorted. Once we solve the subproblem of size n minus 1, all the n minus 1 elements will be in the sorted order. Once the n minus 1 elements in the smaller subproblem are sorted, we need to establish a relationship with the original problem of size n. So the original problem of size n has one element which needs to be inserted in any one of the possible n minus 1 positions in the solved subproblem of size n minus 1. So therefore this is called as an insertion sort. So we will have to find a suitable position where this one element of the bigger problem has to be inserted. It can be inserted at the last, in between any of the two elements, or at the first position. So that is how insertion sort works. An obvious question arises, how are we going to solve the subproblem of size n minus 1? To solve the subproblem of size n minus 1, we are going to reduce it to subproblem of size n by n minus 2. n minus 2, we will reduce it to n minus 3. So we will keep on doing this, and finally when we get a subproblem of size 1, the subproblem of size 1 will already be solved. Then we will come in the reverse fashion, wherein we will take a subproblem of size 2 and we will solve that, then size 3, solve size 4. In that particular fashion, we will solve the entire problem. So say for example, if we are given some numbers 4, 9, 8, 3, 6, to solve these 5 numbers in insertion sort, what we do is we reduce it to a subproblem of size 4. Okay, so this subproblem of size 4 will be solved. So let us assume it is solved. 3, 4, 8, 9. Okay, so now we need the subproblem of size n minus 1 is solved, and we have a problem of size n. So what is the relationship between the solved subproblem of size n minus 1 and the original problem of size n? This one element has to be inserted somewhere, okay, in this solved subproblem. So how are we going to do that? We have to find a suitable position. 3, 4, 6 has to come in between. So 6 will be inserted in this particular position, and we get the sorted list like this. Now, to find the position to insert 6 in this sorted subproblem, there are 3 approaches. One is, we can start comparing the element that we need to insert from the first element present in the sorted list, okay, until we encounter an element that is greater than or equal to the element that we want to insert. That is, we will start scanning from the beginning, and when we find an element that is greater than or equal to 6, we stop and we will insert it one position before that. Okay, so like we compare 6 with 3, 6 is greater, so 6 has to be inserted somewhere later. We will come here. 6 when it is compared with 4, 6 is greater than 4, so 6 needs to be inserted somewhere later than 4. Therefore we come here, and when we compare, we encounter an element that is greater than 6. Therefore 6 has to come somewhere before 8, and we insert 6 here. That is one possibility. Second possibility is, we compare from the last element. 6 is compared with 9. So we keep on doing this until we find an element that is smaller than or equal to 6. When we find such an element, we will insert 6 to the next position, so that it will be in the final sorted position. So that is, we compare 6 with 9, and we find that 6 is smaller than 9, so it has to come somewhere before 9. We compare 6 with 8, 6 is smaller than 8, it has to come somewhere before 8. We will compare with 4, and we find that 6 is greater than 4. So therefore we will insert it at the next position, that is here. 6 will be inserted and it will be sorted. Or alternately, what we can do is we can apply binary search, because in this particular in both these techniques, the time taken may be linear, because in the worst case the element may be inserted at the top position and we'll have to compare with all the other elements, so it may take linear time to insert. Therefore we may think that we can apply binary search. We can find a suitable position by applying binary search because these elements are already sorted, and finally insert 6 here. That is called as binary insertion sort. But if we look at all the three techniques that are available for inserting the element, comparison from the bottom will be more efficient. Why is that? It is because when we compare and find a suitable position to insert 6, there needs to be a empty slot to insert 6. Obviously there won't be any empty slot for inserting 6 because these elements will have one position each for one element. So therefore there won't be any empty slot in between. So we need to create this empty slot. So to create this empty slot, what generally we do is, as soon as we compare and find that these elements are out of order, we are going to bring this element one position downwards. Because one thing is for sure, 6 is smaller than 9, its position is somewhere above 9. It may be immediately above 9 or maybe much more above. But one thing is for sure, it is above. So therefore what we do is, we will bring 9 down. We won't move 6, we won't swap 6 and 9. We won't move 6 here because this is not the place for 6. 6 may go much more higher in the list. So since this is getting overwritten, we will copy it to one temporary variable. Okay, so 6 value is copied to some temporary variable and this element is brought down. Then this 6 is compared with the next element, 8. So when we compare with 8, again we find that 8 is greater than 6, it has to come below. Therefore 8 will be moved here. Then when we compare 6 with 4, we find that 6 is greater than 4 and it has to be stored in a position 1 greater than whatever 4 is present, and already we have an empty slot because in both these positions we have 8. So therefore one of these elements we will be overwritten and 6 will be inserted there and 4 and 3 will remain here itself. So therefore insertion comparing from the bottom will be more efficient out of the three methods that are available for implementing insertion sort. Okay. One more observation what we can make in insertion sort is, now suppose the fifth element is 9, let us assume. These are the elements. Okay. When you compare it with the very first element and find that it is greater than this element, there will be no need for us to compare it with the elements that are present before it. Okay, that because since this list is already sorted, if the element that we are comparing is greater than the last element, then obviously it will be greater than all the other elements and we stop there. We don't continue our comparisons further. Okay, so now this is the working principle of insertion sort algorithm. We will take the same example 4, 9, 8, 6, 3. Okay, and we'll see how we solve this using insertion sort. So to solve a problem of size 5, we need a subproblem of size 4. 4 we need 3, 3, 2, 2, 1. So one element is already sorted. So since one element is already sorted, we will go to a subproblem of size 2. So when we go to a subproblem of size 2, we will place a pointer, I pointer, and this I pointer will serve two purposes. One is it will keep track of the passes. So this is the first pass that we are doing. We don't do any pass for a subproblem of size 1 because one element is already sorted. We will directly take a subproblem of size 2. So it will keep track of the passes. Okay, this is pass number 1. And the other thing is it will tell the index of the element that needs to be inserted in the smaller subproblem of size n-1. So it tells that the second element needs to be inserted in a subproblem of size 1 where it should be inserted. Okay, let us see that. So for that we need to compare this 9 with all the elements that are present above 9. In our case there is only one element, but as the problem size grows there will be more number of elements. So therefore we will place a pointer j to point to all those elements that are above 9, the element that we need to insert. Okay, and as I already told you, this element may have to be copied down. We will copy this to some temporary variable b is equal to 9. Okay, so now we compare 4 and 9. When we compare 4 and 9, we find that 9 is already greater than 4. Therefore the smaller subproblem is already sorted and it is greater than the last element. Therefore 9 has to be present there itself. So we will leave. The subproblem of size 2 is solved. So this is pass 1 of insertion sort. Okay. Next we need to go to a bigger problem of size 3. So when we go to a bigger problem of size 3, we have 4, 9 and 8. These two are sorted and this is the element that needs to be inserted. So we will place I pointer over here. We will place a j pointer over here to point to the first, that is the last element in the sorted subarray, and then this j pointer will keep moving upwards depending upon the value of 8. So now since these elements may come down, we will copy it to 8. When we compare 8 and 9, we find that 8 is smaller than 9. So which prompts us 8 needs to be moved above 9. So therefore what we do is we bring down 9, like I told earlier, 4, 9, 9. 9 is brought down. Okay. So now since this is overwritten, we have copied it to some temporary variable 8 and we compare this 8 with the next element. Okay, j will be decremented, so we'll compare with the next element. When we compare 8 and 4, we find that 8 is already greater than 4, therefore 8 has to come after 4. So after 4 we need one location. Since 9 is already moved down, this location is empty and therefore 8 will be moved here and these three elements are sorted. Okay, so this is pass 2 of insertion sort. And for pass 3, we take these three elements, the subproblem of size 3 which is sorted, and we will take 6, the fourth element that is to be inserted in the sorted subarray of size 3. I pointer pointing to the fourth element that needs to be inserted and indicating that it is the third pass, the j pointer to point to the element that needs to be compared with this. So now since this will be moved down, 6 will be copied to a temporary location V and we compare 6 and 9. When we compare 6 and 9, we find that 6 is smaller than 9, therefore it has to come somewhere above 9. So what we immediately do is, we will copy 9 to one location downwards, okay, and decrement j. Now we compare the same element, 6 with 8, because this is the element that needs to be inserted with 8. When we compare again, we find that 6 is smaller than 8. So 6 has to come somewhere above 8. So therefore 8 also needs to be copied down. Already a temporary location is created over here. So therefore 8 will be copied. 8 will be brought to the one location downwards and j will be decremented. So when j gets decremented, it will be pointed to the first element. So now 6 is compared with 4. We find that 6 is greater than 4. So 6 has to come to a position 1 after 4. So therefore this is the empty slot that we have. So 6 gets inserted here, 4, 6, 8, 9, and you can see these 4 elements are sorted. So this is pass 3 of insertion sort. And we will come to the last pass, 4, 6, 8, 9, and we have 3 which has to be inserted. Okay, so I will be pointing here, j will be pointing here, b is equal to 3. This number will copy because we have seen that elements from the top will keep flowing downwards. Okay, so when we compare 3 and 9, we find that 9 is greater than 3, therefore 9 will come downwards. 4, 6, 8, 9, 9. J will be decremented, j will be pointing to 8. We compare I, V with j. 3 and 8 when we compare, we find that 8 is greater than 3, so therefore 3 has to come somewhere above. We will bring it down, 4, 6, 8, 8, 9. Then 3, j is decremented, 3 is compared with 6, once again 3 is smaller than 6, it has to go above. We will bring it one more position down, 4, 6, 6, 8, 9. So every time you can see, if that element is larger, that is coming one position downwards and pushing all other elements one position downwards. So finally j comes to the first position, 3 and 4 are compared, 4 is also greater than 3, 3 has to come somewhere above 4, so therefore this will also be pushed downwards along with all the other elements, 8, 9. And now we try to decrement j and we find that there are no more elements to compare, so therefore whatever position that is available to us, that is the position where 3 has to be copied, 3, 4, 6, 8, 9, and we can see this 5 elements are sorted. This is pass 4 of the insertion sort, and all the 5 elements are sorted. So this is the unsorted array which we gave as input, and this is the sorted array after applying insertion sort logic. Okay, so like most of the other sorting algorithms, insertion sort also requires n-1 passes to sort a list of n elements. We will see the insertion sort algorithm. So how does the insertion sort algorithm look like? Algorithm insertion sort. So insertion sort, which will take an array of n numbers indexed from 1 to n. Okay, so we will place a I pointer which will start from the second element, because the first element we don't have to do anything, it is already sorted. For I is equal to 2 to n till the last element. Okay, what we are going to do? So as soon as we place the I pointer, what we do? We copy the element pointed to by I, that is the element that needs to be inserted to a temporary variable called as v, because the elements from above may keep coming downwards, so therefore this will be overwritten. So we have copied here. We place a j pointer, j is equal to I minus 1 above I. Okay, then we will keep comparing the element pointed to by the j pointer with v. How long we keep doing this? For until either we come to the top of the list, or element happens to be greater than the element that we need to insert. So therefore, while j is greater than or equal to 0, as long as j is greater than or equal to 0, we have not come to the first position, we will keep continuing, and a of j happens to be greater than v. Okay, that is the element that is to be inserted. So a of j is greater than v. So therefore, what we will do, we will push all those elements one position downwards. A of j plus 1 will take the element which is present at j, and j value will be decremented by 1. J is equal to j minus 1. So we keep doing this until these conditions hold good, that is we reach the top of the list, or this element becomes less than the value that we want to insert, so that we can be inserted there. So once we come out of this loop, we know where to insert that value v, that is nothing but the position j plus 1 will take the value v. So that is where we are going to insert v, and this we do for n minus 1 times. As we have seen, all the elements will get sorted. Okay, so this is the algorithm for insertion sort. What is the efficiency of insertion sort algorithm? Does insertion sort algorithm have best case, worst case and average case efficiencies? In fact, insertion sort algorithm does have best case, has best case, worst case and average case efficiencies, because the number of times the comparison operation performed will depend upon not only on the input, but also depends upon the order of the elements in the sorted subarray. Okay, so we will go step by step. What is the first step? Input size. So input size will be the number of elements in the list, number of elements in the list n. Next, we need the basic operation. What is the basic operation? Basic operation here will take as the comparison operation. Comparison operation, that is a of j is greater than v. Okay, in the while loop we have this condition a of j greater than v. There are two comparisons, j is greater than or equal to 0, a of j greater than v. We can take both of them as the basic operations, but j greater than or equal to 0 is just decrementing the index until it reaches the first position. But a of j greater than v is the one which is actually checking whether we should enter the loop and move the elements down or not. If we find a larger element, then it will stop. So therefore we will consider this as the basic operation. Okay. Next, 3, we need a function to count for number of times this comparison operation is performed. let C of n be the number of times comparison operation is performed. Okay, so number of times comparison operation performed depends on the order of the elements other than the input size. Therefore, the algorithm as best, worst and average cases. So we need to analyze the efficiencies of the best, worst and average cases separately for this. So first we'll analyze best case. So when does the best case occur for insertion sort algorithm? For most of the problems, the best case will be the problem solved. Okay, not always, but most of the times. So the best case, it occurs when the elements of the list are already sorted. Okay, so something like we have 1, 2, 3, 4, 5 as the input. Okay, so what we do is first we'll place the I pointer here, we place the j pointer here, we'll compare 1 and 2 and we'll conclude that 2 is greater than 1, we'll leave it there. Okay, then next we will take a subproblem of size 3, we place I here, we place j here, we'll compare 3 with 2. After one comparison we'll conclude that these elements are already sorted. So therefore we will move, we'll take the next bigger problem, we'll place I here, we'll place j here, 4 will be compared with 3 and we'll find that 4 is greater than 3 and therefore nothing needs to be done, no more comparisons needs to be done. We'll finally take the problem of size 5, place the I pointer here, j pointer here, and as soon as we compare 5 and 4, we conclude that the elements, this is greater and it need not be compared with any of the elements present above. So therefore, in each pass we will be doing only one comparison and concluding that the smaller subproblem is already sorted. So this is when the best case occurs for insertion sort. Okay, so therefore C of n is equal to summation. There are two loops as we saw there. One is the I loop and the other one is the j loop. Okay, so I loop will start from 2 to n minus 1. Okay, in the j loop, if you can see, j value starts from I minus 1. Okay, and in the best case, it ends at I minus 1 itself. Okay, so if we have a subproblem, if we have a subproblem of size 4, j will be at index 4 and j will not even go to 3. So it will start at 4 and it will end at 4 itself. So it will not even go to 3. Same thing for all the lower subproblems also. When you take a subproblem of size 3, j will be at index 2 and it will remain at index 2 itself. It will not go to index 1. So therefore j value will be from I minus 1 to I minus 1. How many times we are performing this comparison operation, a of j greater than v, we are performing only once. When we solve this, the outer summation will be as it is, I is equal to 2 to n minus 1, upper bound minus lower bound plus 1, I minus 1 is the upper bound, minus lower bound, I minus 1 plus 1. Okay, you can see this I minus 1 and this minus I minus 1 gets cancelled and this will be just summation I is equal to 2 to n minus 1 of 1. So this is the same thing. So only in the I loop, in each pass we are doing the comparison operation only once. Okay, so therefore that is equal to upper bound n minus 1 minus lower bound minus 2 plus 1. Okay, so this plus 1 and this minus 1 gets cancelled. It is equal to n minus 2. When we eliminate this constant, we will get it belongs to theta of n. Okay, so the best case of insertion sort is linear. This is one unique feature about insertion sort, that is in the best case it has linear efficiencies. no other algorithms based on comparison as linear efficiency in any case. At least insertion sort as linear efficiency in the best case. It may look like it is not useful, but in some algorithms wherein the input elements are almost sorted, insertion sort has very good performance because it has a linear efficiency. Let us see when does the worst case occur in linear search, in insertion sort algorithm. Worst case of insertion sort. It occurs when the elements of the list are sorted in reverse order. Means if you want to arrange the elements in ascending order, all the elements will be in descending order. It will be sorted in the reverse order. So if you want to arrange the elements in ascending order, the input will be like 5, 4, 3, 2, 1. So what happens in this case, if you can see, every time when we are trying to insert an element, that element moves to the top location of the list. Okay, so therefore it will have to be compared with all the elements that are present in the list to be inserted. So first time when we take a subproblem of size 2, I will be here, j will be here, 4 will be compared with 5, there is only one element, so it comes to the top and 4 and 5 will be here. Next when you take 3, you can see 3 will be compared with 5, 3 will be compared with 4 also, and only then 3 will be inserted at the top position. Okay, so now we have 3, 4, 5 and we have 2. Now also we can see 2 will be compared with 5, it has to come before 5, 2 will be compared with 4, it has to come before 4, 2 is to compare with 3, it has to come before 3, and finally it gets inserted at the first position. Every time all the elements will be moved downwards. And in the last pass, when you have to insert 1 will be compared with 2, it has to come above 2, 2 is got already inserted there, so 1 is here, 1 is compared with 5, 1 has to come above 5, it is compared with 4, it has to come above 4, with 3, above 2, and finally 1 will be inserted at the top. So therefore in every pass, the element that has to be inserted will have to be compared with all the other elements that are present above it, and it will finally get inserted at the first position. So this is what happens in the worst case. So that is what we can observe when all the elements are in the descending order. Okay, so therefore we have C of n is equal to summation I is equal to 2 to n, and J loop, it will start from I minus 1 and it will go up to a value of 1. Okay, when there are 5 elements, it will start with the 4th element and it will stop at first element. When we have 3 elements, it will start at the second element and it will stop at 1. Always it stops at 1. So it starts at I minus 1 and ends at 1. We can write it in the reverse order because it hardly matters. We need to count how many times basic operation is performed. So j is equal to 1 to I minus 1. Basic operation is performed once. So when we solve this, let the outer summation be as it is. I is equal to 2 to n. This upper bound minus lower bound plus 1. Upper bound is I minus 1. Minus lower bound is 1 plus 1. So the plus 1 minus 1 gets cancelled. We have summation I is equal to 2 to n I minus 1. We will apply the summation separately. Summation I is equal to 2 to n of I minus summation I is equal to 2 to n of 1. Okay, so this is nothing but 2 plus 3 plus 4 up to n. So for this we know formula is n into n plus 1 by 2, and since the series starts from 2, we can subtract 1 from this because this is for summation I is equal to 1 to n. Okay, and here we are adding 1 how many times? From 2 to n. So therefore this will be nothing but minus upper bound n minus lower bound 2 plus 1. So when we solve this, we will get it as n squared plus n by 2 minus 1 minus n minus 2. This minus 1 and this plus 1 can get cancelled, minus n minus 2. And now we can see we can eliminate the constants. N squared is the higher order term, lower order terms we can eliminate. So all these constants when we eliminate, we find that the insertion sort belongs to quadratic efficiency class. That is, its efficiency is theta of n squared. Average case analysis, we have already discussed, it is not that straightforward. We need to consider the possibilities of the key elements being out of order with respect to every pair of elements. Okay. However, if we perform an average case analysis of insertion sort, we will find that even in average case, insertion sort is a quadratic algorithm. So in the best case, insertion sort is a linear algorithm. In the worst and average cases, it is a quadratic algorithm. So the worst case efficiency of insertion sort is same like bubble sort and selection sort algorithm. Thank you.